Hi, I'm Dave Reinkensmeyer. I'm a professor at University of California at Irvine. And when I think about the next generation of enabling technologies for people with a disability, I think about trying to better understand the science of people, practice, and plasticity. So I got into working on technology for people with disability when I was in graduate school, UC Berkeley. And I met another graduate student who had cerebral palsy. And she was looking for someone to help one night a week to cook and help feed her. And as I did that, I said, wouldn't it be cool to make a device kind of like C3PO here that could do tasks for you and help improve your independence? And I realized that was a very difficult task. But there was another thing that I realized that people with impairment needed, which was to exercise and to get rehabilitation therapy. And that could improve life and function as well. And so I started working on devices like this. This is from a music video with Dr. Dre and Eminem, where they used a robot from our lab. And in this video, Dr. Dre goes through a serious car accident and then wakes up and goes through intense rehabilitation, and it gets into our device for a little bit to help with that. But the idea is that could we make devices that could help people recover to their full potential after injuries and different diseases? So I started focusing on people who had had a stroke. Amazingly, about 1 in 6 people worldwide will have a stroke. Strokes often affect the area of the brain responsible for motor control, and that causes impairments on the opposite side of the body. Most people recover to some degree, but that recovery is highly variable. And so recovery might look like this for someone who is fairly impaired after the recovery. So I'm asking her to touch her chin. You can see she has a lot of trouble lifting her limb.
That's good.
I became interested, really obsessed with how do you get into the state? Can you get out of it? So we started developing robotics technologies that could assist people who are impaired after stroke in performing rehabilitation exercise. So this is a robot called Neurobiology. It's compliant. This was developed with Eric Wolbrecht. You can see in this video that she's trying to reach objects, do a shopping task, and she's gripping and releasing them into this cart. And what the robot has its own neural network, and it's learning a model of how much assistance she needs, and then trying to provide just as much assistance as needed as she does this task. Here's a typical robotic therapy result. This one from Neurobiology, the robot I just showed you. This is delivered with Vicky Chan, who's our research physical therapist. But we had 26 individuals with chronic stroke, exercised for 2 months. Half of them got assist as needed robot training, and then half got conventional tabletop therapy with a therapist. And you can see this is the change in their arm movement ability. It's called the Fogelmeyer scale. It goes from 0 to 66, and about a 3-point change in that. A clinically meaningful change, which you get at by asking people, at what point do you feel like this is really helping you? It's about a 5-point change. This is a modest change. You can see the standard deviation is here, so this is normally distributed. You get about 20 or 30% of people achieving that 5-point change. Okay, but you have a high variability as big as the treatment effect here. So we had a positive benefit, and we said, can we get this out to people? And I gave a talk, and it was seen by Gary Colombo at Hokoma, a Swiss company doing robotic therapy devices, and they developed this device, Armeo Spring. They developed it based on a device we had developed that just used springs instead of actuators. And we had worked with Tariq Rahman at AI DuPont Hospital for Children. And this now has adjustable arm support, and you enter into this sort of computer gaming environment and do the same sorts of exercise. So this has now been commercialized. It's in about over 1,000 rehabilitation facilities worldwide, studies published. And it's a quite expensive device, but we're starting to see or get larger scale data from multiple sites with this. We try to push and make things even simpler. We're working with Nitzan Friedman, who was a Ph.D. student in my lab. He helped invent this device that just takes wearable fabric and it detects when you're making different grips. And we connected it to the 3rd most popular video game ever invented, which is Guitar Hero, and had success where people really wanted to use this and actually did more practice than we asked them to when they took it home. And so this was commercialized. We formed a startup company. It's been commercialized, and now there are about over 7,000 users. An interesting thing happened when we first started selling that. Only about 10 or 15% of the people that were calling the company to see if they could use it could actually use it, had enough hand movement ability to use it. So Flint invented this technology, which is, it's a sensor that has a force sensor in it and an IMU, and they worked with an occupational therapist to develop about 40 different exercises you can do with it. And you can see here's a flipping one, and back here's another exercise in the background. And there's about 8,000 users of this exercise now, or of this device, the Fit.me plug. So the summary, kind of that first part, and tell you how I got to where I am is, so these robotic and sensor-based practice technologies are now proven to help produce modest positive results when people with motor impairments use them to train. It's still very highly variable. And these devices are starting to be deployed at scale through inventions in my own lab and inventions coming out of other labs. Now the question is, how do we make these devices better? And I'm going to propose 3 tasks. And this is kind of a brain dump, so I'm just going to let it all out and give you my 3 tasks for the future here. The first is, I want to better model the drivers and limiters of motor plasticity after nervous system injury. I think this is fundamentally a computational neuroscience problem. And by that, I mean, I think we need to mathematically model the mechanisms of plasticity and motor learning and drive those models with the real data from actual movement practice derived from machines or sensors in the course of rehabilitation. And I put a reference here to a opinion paper or kind of review paper I wrote with a variety of leaders in the field, where we're trying to make the point that this is what's missing right now to help guide the design of machines and algorithms that really optimize recovery. Just as an example, the types of things we need to study, we did a study of finger training after stroke using this finger robot developed by Eric Wolbrecht again. And they played Guitar Hero for 3 weeks. Our primary outcome was how many blocks they could pick up and move over a divider in a 60-second period. And what we showed here is that the baseline proprioception, so this is their ability to sense where their fingers in space, was a strong predictor, 40% of the variance of their motor skill improvement. We measured proprioception with the robot itself. So at baseline, we asked them to try to sense when their fingers were crossing each other as we use the robot to slowly move fingers past each other. Of course, they're doing this without vision. So this relates to this idea of computational modeling, because we got this idea because if you're learning through sort of a reinforcement learning process, you need feedback about, am I moving better each time I move? That's probably given to you by your somatosensation, such as your proprioception. So indeed, here we confirmed that if your proprioception is messed up, then the robotic training doesn't benefit you very much. And we worked with Steve Kramer, a neurologist now at UCLA, and we did brain imaging and showed that out of about 50 possible predictors, it was the injury to your somatosensory system that most strongly predicted your motor skill improvement after training. So what's amazing about this is finger sensation really matters, but it's clinically ignored right now. It's typically not treated and it's not measured. Task 2 is to understand how to maximize uptake of practice technologies. So let's take an 8-week snapshot of about 2,500 users of the Fit.me pucks. And you can see here on this is on a log scale. A lot of users didn't do that many reps down here, less than 100, but over 10,000 here, you get a group of people doing quite a bit of exercise. So what drives this type of distribution? Why does that distribution matter? Well, what I think is now a classic paper by Jeffers, they looked at a rat model of stroke, and they looked at how the number of reaches that a rat does every day affects their ability to do a skilled reaching task. And you can see it has a hockey stick shape to it, meaning that you can do 100, 200, 300, even 400 reaches per day. It doesn't really change very much your skill. You need to get up into that 500, 600, 700 area in order to have a change in skill. And I think a lot of rehabilitation takes place in this flat part of the curve, and we really struggle to get people up, and people struggle to get up into this region where they can drive plasticity through practice. I'd like to make the point that, using devices like Fit.me or the Music Glove that are getting out there, or Army of Spring, well, these can become tools for doing new forms of rehabilitation science. So as an example, when we look at, Fit.me users and who practiced more, we had the hypothesis that maybe your success at the game during your first week of practice influences that. And indeed, this is the probability of achieving certain levels of practice over the course of several weeks. And this is your success rate at leveling up in the game. And if you did perfectly 100% leveling up, you tended not to exercise very much. It was like too easy for you. And then people who had struggled to level up, they tended to exercise less as well. So we see this kind of optimal level, success level, about 90 to 100%. So very interesting. We could start getting at what are the factors that determine amount of practice, and that amount of practice, we know you have to get very high amounts, much higher than what we're currently achieving to drive plasticity. Task 3 is to develop softer, lighter, and more powerful actuators that enable what I'm calling activity success. This is a picture of my parents taken about 2.5 years ago at a beach here in Orange County. They both passed away now. My mom developed balance problems and stopped exercising really, and then made the balance problems worse. And she fell and eventually passed away from the injuries due to those falls. My dad developed Alzheimer's disease, started having cognitive impairment, and also started falling, and then eventually passed away after being injured in falls and also being weakened and getting an infection. And in this process, really there was no technology that I found that could really assist them. Now I could be with them and watch them and physically help them. Okay, but there was no robotics technology that was really suitable that you could put on a person or that could help them to stay stable and walk. And I really think that's because there wasn't, the type of actuators we have available right now just aren't light enough and soft enough and powerful enough compared to the actuators in a human body, where I, in my actuation system, I could, with my intelligence, my actuation could walk with them and aid them. Why does that matter? I think one reason is because of what my colleague Nicholas Schweighofer at USC calls the threshold hypothesis, which I think is a general law of activity in rehabilitation. But this, I'm going to apply it here in the concept of upper extremity movement after stroke. And what this law says is that there's a level of functional ability that you need to have with your limb in order to actually use the limb at home. Here's a device called the Manumeter that we developed with Diego Schwartz-Lucina. The ring's a magnet, and we have a magnetic array back here, and we can detect how much the person's using their hand. So we gave that to 29 people who had stroke. They used it at home. We measured their function of their hand in the clinic on the box of blocks test, and you can see that you could have considerable function, but you really don't use your limb at home hardly at all. And I think that leads to this kind of vicious cycle where neuroplasticity works against you, as Schweighofer has pointed out. And what you want to do is get into the situation where you have enough function that you're actually exercising at home and progressing as you go. So just to summarize, I think, practice technologies that provoke plasticity, they show promise for helping people achieve their neural potential. They're starting to be deployed at scale. We can start doing new types of rehabilitation science on a scale not really done before. And to optimize these tools and really meet the neural potential, we need to understand people, practice, and plasticity, and how these three things interact together. And I do think better actuators can help us destroy this idea of this threshold law of activity and help people to be more functional and promote beneficial neuroplasticity. Thank you very much.